Welcome back, everybody, and thank you for coming to this session. I hope you're all having a wonderful time here at I/O. You know, one of the things we think a lot about at Google, when we think about the impact of AI, we think about how it's going to advance the possibilities for people, individuals. We also think about how it can enable and empower the economy. We also think a lot about how much it can advance science and help us address pressing challenges for society. Now, you heard a little bit of this on the stage yesterday from Demis, but this session we wanted to spend more time focusing on that last part, which is how we see AI advancing and driving major landmark advances in science and helping us tackle some pressing societal challenges. We have extraordinary teams across Google and Google Research, Google DeepMind, work of research scientists and others working on these hard scientific problems that are important for society and for humanity. And I'm thrilled that I have several colleagues here. Pushmeet, I'll introduce each of them properly when we start the conversation, but Pushmeet, Joëlle, and our friend and collaborator, Anima, Anandkumar from Caltech. So why don't we jump into it? By the way, if you want to find out more about our AI and science work, I think there's a QR code that's available. It'll give you a lot more details about some of the extraordinary work that my colleagues and all of us are doing at Google. Let me start with you, Pushmeet. So let me actually introduce Pushmeet. So Pushmeet Kohli is the Vice President for Science and Strategic Initiatives at Google DeepMind. He works on a lot of the foundational research advancing science across multiple areas, biology, mathematics, physics, and so forth. But let's get into it, Pushmeet. A lot has happened in the last year. What are some of the things you're most excited about that you've worked on, you and your colleagues have worked on?
Yeah, so I think, James, one of the first things that we have to talk about when we are talking about AI for science is AlphaFold, because it's in some sense been a key milestone and a key sort of example of what is the potential of AI for science. What AlphaFold has achieved is solve this amazing problem in biology that has implications across a whole spectrum of different application areas, from drug discovery to sort of developing enzymes for sort of decomposing plastics, to really uncovering a lot of mysteries of synthetic biology. Now, what AlphaFold 2 did was find the structures of proteins. Last year, we expanded that with AlphaFold 3, which goes beyond the structures of proteins and sheds light on the structures of all the other biomolecules in the body. Like, how do proteins interact with small ligands, which are very relevant for drug discovery? How do they sort of form complexes? What is the structure of those complexes? How do proteins interact with nucleic acids, RNA and DNA? So really expand our ability to think about structural characterization of biology. Biology in itself is one of the most amazing application areas for AI, given the complexity that it has. And what we have been able to do is build on top of AlphaFold to not only make progress on structural biology, but take on many other different tasks. So two good examples in biology have been our work on understanding the genome. What is the effect of missense variants or mutations in the genome? So we had a model called AlphaMissense, which was built on top of AlphaFold, which is able to predict whether variants or mutations in the genome would be pathogenic or benign. And this is already seeing impact on diagnosis of rare diseases in the medical and clinical context. Another example is AlphaProteo, which is, again, leverages AlphaFold 3 and is now able to think about how do you synthesize binders for new proteins, right? So this is like coming up with completely novel proteins that do not exist in nature, that we have purposefully designed to solve certain tasks, like binding to specific targets. And that opens up like a variety of different applications, both for drug discovery as well as for many other application areas as well.
Yeah, you know what I find extraordinary, I think you all know this. So AlphaFold is our system that won the Nobel Prize, that Demis and John Jemper got a Nobel Prize for. But what I find extraordinary is the fact that now more than 2.5 million biologists around the world are using it. And these are people in over 190 countries. And I think that's extraordinary, how it opens up the possibilities for science. But Joëlle, let me come to you, because you're also spending, so I should introduce Joëlle. So Joëlle is the senior director at Google DeepMind. She works on a lot of the foundational research in healthcare and the health medical space in particular. She also leads a broad range of teams across Google, building kind of extraordinary applications and solutions. What have you been most excited about in the last year, Joëlle?
Well, thanks, James, and thanks for having me. Hi, everyone. It's really great to be here this morning. It's a tough question because we do so much across the spectrum in healthcare. I think we've published more than 50 papers last year alone. But if you're asking me to pick one, I think I'll cheat a little bit because I'll talk about a family of papers around AMI, our Articulate Medical Intelligence Explorer. So you can think of it as a large language model that we've specifically designed to be able to do diagnosis, right? So in some ways, augmenting or replacing what a PCP would do, what a physician would do. And this is obviously a research project, right? We're really exploring the art of the possible with that research project. A year ago, we had done maybe the initial paper that was a very simple dialogue system, text only. And over the last year, we've, for example, looked at what it could do in specialty care, both in cardiology and in oncology, with our colleagues at Stanford and at Houston Methodist. So we're working with physicians and clinical teams to see how for specialty, when you really need a lot more knowledge, our language models can also do diagnostic reasoning in a way that is on par better than physicians. We've also continued to push that series of paper to give eyes and ears to AMI. So not just have things that are text only, but also have the ability to upload various documents and reason on those documents. And then last but not least, we've started a study with Beth Israel Medical Center to be able to see what happens when you start deploying this in clinical settings, under RRB as a research project, but to see under physician supervision when this is able to either accelerate or augment the diagnosis a physician would be doing. So a lot of exciting progress with AMI over the last year.
Yeah, no, actually, well, I know exactly why you found it difficult perhaps to pick one, because there's so much. One of the things at least I was particularly thrilled about last year was some of the work in tuberculosis diagnosis, for example, using AI tools, just because something like 30 to 40% of the world's population that has TB goes undiagnosed. And often that's because they live in places where the resources are not available. So that was extraordinary. Anima, you've been, so Anima, again, I keep forgetting to introduce my panel as well. So Anima is a professor of computer science at Caltech, and she's done some of the most groundbreaking work around AI advancing kind of how we understand physical systems through these incredible techniques called neural operators. But you should talk about what have you been most excited about in the work you've done in the last year?
Yeah, thank you, James, and thank you for having me here. It's such an exciting time for AI. And to me, the passion has always been how we can advance pretty much all of science, right? And build broad frameworks and foundations to be able to do that. And to me, now we are seeing the entire scientific method itself getting appended with AI, right? Because the traditional approach has been, right, scientists have ideas, hypotheses, you go test it, you get feedback, you come back, and you redo the whole process. And of course, now with approaches like co-scientists, AI can come up with all kinds of new ideas, right? But the bottleneck still remains that if you had to go into the lab and test, build, fabricate, do this for every single hypothesis or idea, it would still be not feasible because that's the critical bottleneck. And so what we've been building is AI that understands the physical world, that can really create very accurate, high-fidelity digital twins of these physical systems, right? To give you an example, we are now be able to design like photonic devices in digital realm, right? And the question is, can we do that with enough confidence that we can, overcome the need for lots of lab experiments so we can go ahead and come up with what the best design is given all the different manufacturing and other constraints. And for the domain scientists that are collaborating with us, this is just an amazing new possibility that they never thought was ever realistic, right? Because the traditional approach is, we already have a current device, let's tweak a few parameters. And again, it's too risky to change too much of the design, so we'll do small tweaks, and we hope it gets better. But the challenge is the lab experiments also don't give you gradients or feedback, so you don't know if it didn't work, why not? Whereas if you can create these now surrogates or models that accurately capture that physical phenomena, and these AI models are differentiable, we can even explore the entire design space and come up with what we think are compelling and the most promising designs. And we were earlier able to do this for designing the medical catheter, where AI was able to understand the fluid flow and come up with the optimized design that reduced bacterial contamination the maximum. And we only had to go to the lab once and test it, and it led to 100-fold reduction in bacterial contamination. And so that, to me, is the promise. As much as we can design in the digital realm with all of its physical complexities and details so that it just works in the physical world. And this is where the techniques of neural operators, in my view, are critical, because the physical world is not just the visible, right? So when we think of the world model, we're thinking of the world we see, but there is the world of the invisible, which happens at so many scales. You can think of like fluids moving, matter deforming. If you go down even further to the quantum effects at these scales that human eyes cannot see. So there are different levels of those complexity you need to capture for different physical phenomena, for different scientific areas.
Right.
And the approach of neural operators can really help us learn across these different scales, because it's not limited to one fixed resolution or one fixed grid, which standard neural networks do. And hence, they can learn any phenomena of any complexity, of any different multiple scales. And that's what a lot of physical phenomena are.
Yeah, no, I think it's quite extraordinary when we think about the generality of these possibilities, but also the idea that we go away from solving problems kind of one at a time and look at all of them. I'm struck by that in your work, but also, Pushmeet, and what you were describing earlier with things like even alpha-missense, where I think before alpha-missense, scientists going one at a time in terms of those genetic coding misspellings had only understood some of the 1%, and then with alpha-missense, you got that up to 71% or 70% of all the missense spelling. So this idea of kind of doing things at scale is extraordinary. But Pushmeet, one thing Eri didn't talk a lot about, and you've been doing, and colleagues have been doing a lot of work, is on weather and climate science, which is another physical system. Say more about some of the advances in the last year in weather and climate.
So I think weather and meteorology and climate, I think these are some of the very important topics that we are seeing a lot that is happening with AI. First of all, there is a lot of conventional computing that has been applied to weather. It's not as if computational methods have not been applied to weather. There has been a lot of investment, right? Weather prediction has been the subject of supercomputer research. There's a lot of computation that goes into it. What we have been able to show in the last couple of years, in fact, have been that AI models, neural network-based models, have been able to produce near-term forecasts that are not only more accurate than these very sort of expensive simulations, but they can be done in a minute on a single chip. That democratizes weather prediction in a way that has not been seen before. Now you don't need a supercomputer to make weather prediction. You can do that on a single GPU or a single TPU, right, in a minute. So that opens up the possibilities. And what we have done is basically with our weather next models, we are actually making these predictions available across the whole spectrum of applications. So people have now signed up through Google Cloud to access these predictions. And our new model, Weather Next Gen, has been able to show that you can track things like cyclones much, much more accurately over longer timescales than conventional systems. And then finally, like work happening across Google, Google Research and DeepMind on neural GCM, these global models, which are similar to, in fact, what Anima has been developing, is they have been able to not only produce good estimates about weather in the short term, but also speed up computations about climate simulations. So also, like, what are the implications of these systems over the long-term horizons of climate prediction? So we are seeing developments across the whole spectrum of the time domain, from near-term forecasting, medium-term forecasting, as well as long-term sort of climate prediction.
No, I think it's extraordinary. It also reminds me of some of the work we've been doing recently, as you know, with around related to climate, around wildfires, for example. So I don't know if folks in the room know. So, for example, we've been doing wildfire boundary predictions now in about 27 countries, which is extraordinarily helpful. In fact, some of these techniques were used in the Palisades fires to actually track the boundaries. And very recently, we actually launched this new system, FireSat, where we put up, it's going to be a constellation of 53 satellites. The first one went up. And the idea with that is that up until now, the kind of granularity of what you could actually look at was fairly coarse. But with these satellites, you'll be able to take a look at areas that are like 5 by 5 meters and be able to make predictions anywhere on Earth. So that's another area related to climate. But just to shift gears a little bit, I mean, one of the things that's been interesting is, in addition to these kind of landmark advances that you've all described, the methods and the ways in which scientists do their work are also changing as a result of all of this. And I was wondering, maybe, Joëlle, you could start this off, but could you talk a little bit about how you see the actual work of doing science changing as a result of AI?
Yeah, absolutely. I think at a meta level, we are really seeing how AI can completely change the way we're doing science. And if you think of what we've published as the co-scientist, right? The idea is to have a system, an AI system that has been specifically designed to help scientists in their work. So think of it as a powerful system that can first, for example, help you understand the whole literature, right? Not just what has been published recently here, but what has been published globally anywhere over the last 100 years, right? And really put all of that into perspective with respect to the question you're currently asking yourself. It can then help you formulate various hypotheses, and that's really leveraging the creativity of large language models. But it doesn't stop there. Once it has all of those hypotheses, it can also help you as a scientist explore each of them and critique them, again, leveraging AI, right? So it will rank them, you can make them compete with each other, and it improves itself so that it starts, as you interact with the system, as a scientist, it's not doing it on its own, but you're really helping. I like to think of it as a new chalkboard, right, or a whiteboard. It's something where you can really bounce ideas and experiment with, but in a much, much more knowledgeable way, and really augment what you can do very quickly. So then similar to what you're saying, you're narrowing down the number of things you really have to go to the lab with to experiment. And so it's what Demis likes to speak about as science at digital speed, right? Because you can do so much based on just the information you have and those tools.
Actually, say a little bit more about the experience with co-scientists, because one of the things that was extraordinary to me, at least, was the fact that in co-scientists, we're able to explore new areas, whether it's in drug repurposing, for example, or antimicrobial resistance, and actually discover interesting new insights. Say more about co-scientists.
Yeah, no, precisely. So I think, with this system, it's an agentic platform. So you have a couple of stages where it's looking at, for example, for a given drug, how can it be repurposed? And you see that for that particular problem, you have a combinatorial space that you have to search through. And that's typically a problem for which AI is very well suited. And so you take this, question and you let the system explore. And what we've been able to do is compare what the AI comes with what has happened in the field, right? And kind of rediscover things that had taken labs, years sometimes to get to. And so it's still in the early days. I think we still have to do a lot of validation, to make sure that, none of those things were in the training data, none of those things could have been, contaminated in any way, shape, or form. So we are really continuing the work to really see, moving forward, if we have with the co-scientist a particular hypothesis, or if it's really truly making us do a discovery that we wouldn't have come up before, that we do that in a way that is also extremely rigorous in its validation. So I also want to really emphasize that, it's again, everything is moving so quickly. We also have to continue to have a very rigorous scientific method to make sure that, we truly have something unique in the way we can do new discoveries.
Yeah. And Anima, how do you think this is changing how scientists do their work?
Yeah. I mean, I think it's given them incredible tools, right? So to kind of reiterate on the weather and climate modeling, in 2020, when we started, with exploring the neural operators we had developed, it had worked well on fluid dynamics more as a proof of concept, and we wanted a real world case. And we had we had collaborators in the Lawrence Berkeley lab, here local, right? And they, then this data set was open, and it was open sourced by the European, premier climate and weather organization, ECMWF. And so we were like, okay, let's try this. And many people discouraged us because this was considered extremely difficult, right? Like high resolution, hundreds of variables. And it has taken weather scientists decades of work to carefully tune physics-based models, which try to model from ground up to get to where we are with the current weather capabilities. But the beauty of deep learning is, as long as the data is there, we can just go try it. And even with our first attempt, what we were surprised was we got to good accuracy, not only of typical weather conditions like here in California, which, honestly isn't that hard to predict, but extreme weather events, right? Storms, hurricanes, typhoons. So because you don't think as a machine learning scientist that you would get that because they are rare events. In the last 4 decades, the data set maybe has a handful of these. But again, the reason why I believe this was possible is because there are clear physical signatures, like hurricanes have this hot and air cool mixing together. So, it is not just the amount of data, it's the kind of like the signatures and how significant are these events, right? And the model is able to pick that up and is able to even do now better than traditional models. And I think that took a lot of weather scientists by surprise. But I'm also very heartened to see how much adoption has happened at a lightning speed, because ECMWF made all these models, our model, and Google DeepMind has done excellent work after that with GraphCast and others. They're available. It built its own model, right? It's declared them as operational, which is the gold standard, meaning side by side, it's running today with traditional models, and weather scientists can make judgments. And the other key is, because of the speed, we can now build much larger statistical ensembles of events like hurricanes, right? Because what you care about is not just one prediction of where the hurricane is going to go, because there's a lot of uncertainty. You look at perturbations of the current conditions and see how many of those tracks are going to land in Florida, for instance, in a very specific region. So each city can then decide, should the evacuation happen, right? If it's 90% versus 60% chance, it's a very different policy decision. But now we can enable that, which was not possible with traditional models. So it's not just, okay, accuracy is somewhat better and faster, but now we can go to the tail events, which is the hardest aspect, and we can come up with accurate, calibrated probabilities of, and assess risk for these events.
One of the things that's been interesting to observe in the last few years is just the one of the changes has been the deeper collaborations that now happen between, my colleagues and I and others, but also with academia. So I think in almost all of this work, there's deep collaboration between, AI researchers and scientists in different disciplines, but also in academic institutions. I think, for example, some of you may have seen some work we published on last year on connectomics, where we tried to figure out the wiring diagram of the brain, for example, at the synapse level. That work was a 10-year collaboration with the Lightman Lab at Harvard, doing these very painstaking kind of foundational work. But I want to come back. Pushmeet, you and I often spend a lot of time talking about mathematics. You all heard about AlphaEvolve yesterday. But I remember, one thing that was striking was last year when, alpha geometry and alpha proof kind of did well enough to compete at the Math Olympiad and compete at the gold level. One of the things that was striking about that, and I don't know if all of you kind of tracked that, was the fact that in a lot of how it did what it did, it used a lot of kind of its own generated examples to train itself. Talk a lot about how you think about the role of data and other things that are critical and new techniques that are emerging as we think about both, not just mathematics, because you and I talk a lot about that, but also other areas of science.
Yeah, so I think when we talk about AI and machine learning, I think data and experience. We don't get insights in a vacuum, right? So insights come from experience, and experience comes from data. And that data could be data that scientists have collected over many, many years, like we did in the case of AlphaFold through the PDB, the Protein Database Bank, or it is experience that has been generated through simulations. Now, across many different applications, whether you look at biology, or another great example for synthetic data generation is in fact fusion. So in fusion, if you want to learn a policy that can stabilize plasma in a tokamak, you have very limited data, because those tokamak fusion reactors run for very few, like a very short duration of time, so you don't have much data to train on. So in our work on the model called Pulsar, where we were training a policy to stabilize plasma in a tokamak, a lot of the training happened on complete simulation data. And the real challenge was, how do you generalize? How do you make the policy so robust that it can generalize and go over the sim to real gap, simulation to real sort of domain transfer, right? That even though that policy has been trained on simulated data, when it is sort of applied in a real reactor, it works. And that is what we showed that it was able to do. Now, we have been able to do this in a whole spectrum of different applications. Even, as you mentioned, in mathematics, where it is particularly sort of relevant, where in the case of alpha geometry, for instance, we have very limited number of geometry problems, even though we have a lot of geometry problems, but the appetite for these models is immense, as you know, right? They are quite data hungry. So we had to generate a large amount of data in terms of synthetically generated geometry problems, which we were giving these models to solve. And that is how the model actually learned itself to solve and get itself much better to reach at a gold level standard on geometry problems. On the other sort of side, there is another sort of element which is test time RL, right? Which was used in AlphaProof, which is when it tries to solve these very hard problems. And by the way, these are incredibly hard problems. Even field medalists wouldn't be able to solve them like sort of as a matter of fact. They would take time to solve these problems. These are really sort of problems at the highest difficulty level. What the model was doing was it was taking the problems, and like a human mathematician, it was seeing if it can solve a simpler variant of the problem. So suppose you have to prove a theorem for all reals. Right. So first you can say, well, I'll not prove the theorem for all reals, I'll prove the theorem for only even numbers. Right. or odd numbers or a restricted domain, and then I can generalize. So this idea of really sort of synthetically generating a lot of variants of the problem, trying to solve them, and in the process learning from that experience to then finally be able to solve the larger, most difficult problem. So synthetic data generation is everywhere in that sense, right?
Yeah, and it's also interesting to see how that mix changes for different kinds of problems between kind of real world training data versus synthetic versus simulated data. But I wanted to come to something I know, Joëlle, you spend quite a bit of time thinking about, which is even as we make all these advances, there's still important things to think about how to be responsible and how to think about responsibility in the science realm. What are some of the things you think a lot about when you think about responsibility with regards to AI and science in particular?
Yeah, and maybe to echo what Pushmeet was saying, right? Synthetic data obviously is something very important as well from a responsibility perspective, because we really want to make sure that what we're building in healthcare in particular is going to help everyone, everywhere. And that's only possible if the data we train on represents people everywhere. And that's really hard because data is scarce and we don't necessarily have it globally. And so something we're doing with data in particular is to see how synthetic data can help us augment, right? So if you have models that have been trained only on a particular demographic, you can perturb the data so that you're on a bunch of dimensions checking what your model would do on that perturbed version of a particular scenario. I talked about AMI at the beginning, our Articulate Medical Intelligence Explorer. And this is a system that we're testing primarily with patient actors, mimicking what's done in medical school. Students learn complicated scenarios with actors mimicking the behavior of a patient going through a particular diagnosis in the way they interact with the physician, because that's really the only way to have something rigorous methodologically, right? And to be able to grade those students, did they react properly when that patient actor forgot to mention half of their symptoms or lied midway through the encounter, etc. So the students really have to learn and have been learning that way for decades now. So we used the similar methodology with our models to also be able to assess them responsibly. The other thing we're doing on a responsibility front, which is really important from my perspective, is to always engage with the stakeholders and the external ecosystem. And in healthcare, it means physicians from a variety of disciplines. It can be ethicists. It's, of course, the big hospital centers, et cetera. And that is also a way for us to make sure that what we're building is addressing real clinical needs, right? And that we're doing it in a way where all of the stakeholders that will have to leverage those systems moving forward help us get the inputs that make us build them in a way that they will be the most helpful to them. So this is something, I mentioned Stanford and Houston Methodist. In France, we're also working with the Curie Institute on various tools to help us make progress in hard-to-treat cancers. And that really brings the whole, the whole spectrum from patient care to the physics that sometimes is needed to all of the biology, that better understanding of the cell, and in really making sure that we've looked at the problem in its entire complexity.
Yeah, no, I'm struck by what you said about this idea of trying to solve for everyone. I'm reminded of the fact that I think people in the room probably know this, but if you remember when the human genome was first mapped back in the early 2000s, I think often we forget that was actually for a single genomic assembly. It was a single genomic assembly. And one of the things we've done in the last year is actually drafted the first reference pangenome that actually has 47 genomic assemblies, which are much more representative of kind of the full genomic diversity of the world, for example, just as a way to expand that. But I want to shift gears a little bit, Anima, and start with you, which is, so as you look forward and you start to look ahead, what do you see in this realm of kind of, what are some of the things you're kind of focused on and excited about looking forward?
I mean, to me, it's like the question of how do we expand our understanding of the physical world, right? And AI that understands it in all of its different levels of complexity And of course, the one big bottleneck, like Pushmeet also mentioned, was the data, right? So if we have the internet with all of it, we could just download and train the model. It's much more straightforward. But we can, even if we know the equations in lots of these physical systems, right, you can go down all the way to quantum scale and say Schrodinger's equation. But even to generate the fully accurate result for about 100 electrons takes more than the age of the universe, right? So all these systems in that sense are extremely compute limited and unrealistic to generate the full accurate data needed to train the models. But then the question is, what levels of approximate data can we give the model? So you know this data is wrong, right? And there's going to be a sim to real gap. But first of all, in simulation, can you refine and give it more and more accurate data? So this notion of curriculum and how do you hopefully have a lot of data that is approximate and only a little bit of like the expensive data that's accurate to fine tune, and you can get the model to behave as the fully accurate system. I think that's the next realm in a lot of these areas. And for us, when it comes to these kinds of multi-scale phenomena like fluid dynamics, we're now able to establish both theoretically and in practice as well that you can now train these models with like solvers that we know are approximate. So you can train them on a coarse grid, and then you can use the same AI model and fine tune it with the fine grid information. Because the idea is if you think of a hurricane and you only look at it as a coarse scale, it gets blurry, right? And without capturing the fine eddies, you can never get to the full accurate path of the hurricane. But now, if most of the way you train with that kind of coarse scale data and with fine scale, with what happens in between those coarse grid, what happens in between, if you can provide that to these neural operators, they can refine internally. As opposed to what people have been doing more traditionally is, let's keep the coarse grid solver and try to correct the effects with another machine learned model called a closure model, or you coarse grain, you average out in some simple way, add it up. But these are hand engineered, right? I mean, mixing across scales doesn't happen in an additive way like people think they do. They're bad approximations. But with neural operators, it kind of has the flexibility to figure out how to optimally mix across scales to fit to the target data and do that with high data efficiency.
Pushmeet, what are you most excited about?
So a lot of things. I think
know you are.
I think what we are sort of really seeing is the confluence of a number of different trends coming together. One is the integration of domain-specific AI models, right? And we have seen these breakthroughs that AI models have made in biology, in chemistry, in weather prediction, in health, right? At the same time, we are seeing these agents which can do hypothesis generation, can operate at the level of basically the scientific process, co-scientist, AlphaEvolve, right? Which really sort of speed up the scientific process. How do these two things come together?
Right.
Where the agents now are able to sort of also integrate these deep domain-specific sort of systems and can communicate across those two very different kinds of cognitive processes, right? And so that acceleration that comes from it, I think, is amazing, and we are already seeing that in the context of AlphaEvolve, right? AlphaEvolve was able to discover, like, it was applied on 50 open math problems. 75% of those problems, it went to the state of the art. 20%, it went beyond the state of the art, right? This is like not one particular problem. This is sort of a wholesale sort of acceleration of a whole sort of area of research, right? So that's what's happening. The other sort of thing that I'm really excited about, in certain domains, we are seeing transformative abilities, right? If you think about materials, the acceleration that we are seeing in materials, it's amazing, right? Like the way we are improving our abilities to predict the stability of materials, their properties, that whole sort of closing the validation loop, all of these things are sort of super interesting and fun.
Well, and I know if we had more time, you probably would have talked also about isomorphic labs and drug discovery.
Exactly. And I think the point is we are seeing AI not just having scientific impact. There is scientific, social, and commercial impact. These things are not in just the lab now. AlphaFold, for example, now we spun off a part of AlphaFold to really focus on drug discovery, and isomorphic is really doing very well in its mission of accelerating the whole drug discovery process. So you are seeing extremely high commercial impact from the breakthroughs from the scientific breakthroughs that have been made.
Joëlle, what are you most excited about as you look forward?
Yeah, no, I think as Pushmeet was saying, right, it's really everywhere, and I think it's moving at an incredible pace. And for me, we launched yesterday MedGemma, which is our open weight model fine-tuned on a medical corpus, and I'm really excited to see what the community will do with it, what developers will build on top of it to then answer particular clinical needs, because I think it's true in healthcare, it's true in the sciences. There's so much to do that I think the more we see, every single specialty and every field kind of redefine itself with AI, that's how we will get to many breakthroughs in years to come that are going to redefine, I think, a lot of our industries even. And I think I'm really excited to really see what the community builds on top of some of the foundationals that we've put in place.
Yeah, I'll just add one other area that I'm particularly excited about, which is we're making so much progress in quantum computing, and we actually have a team, Quantum AI, which is focused on that. So even before we get to a fully error-corrected, fault-tolerant quantum computer, we're going to be able to start to do some science along the way. So I think in the next year or two, we're going to start to see algorithms, even with these noisy quantum systems, that start to work on actual scientific problems. We know a lot of science areas like chemistry are inherently quantum chemistry and so forth. And so there's a whole set of areas that are going to be possible. So I'd say watch this space with regards to quantum also advancing science. I think in the last minute that we've got, I thought we might do a quick lightning round, which is perhaps a bit more of a personal question to each of you. If you think about the next, I'll say 5 years, are there one or two problems you personally would like to see breakthrough progress on? Either you want to work on them or you would like to see breakthrough scientific problems. What will be on your list? Do you want to start?
Yeah, to me, it's building physical AI in all of its different levels of complexity and scale, right? So multi-scale, multi-physics. So when we think of world models, not just the visible world, but the invisible as well.
Okay, Joëlle?
You like us picking only one. It's always really hard.
You can do two.
I can do two. No, I'm in the Earth modeling. I'm really keen to see whether AI is going to help us better predict earthquakes, for example, or things that are can have an impact on all of us here in California in particular. And I think those are really hard problems that we've tried for years to really get better at, and seeing how. I think we are at the beginning of something where we could really have major breakthroughs. Something more personal and that we're working on, I mentioned cancer already. And if you think of cancer, when Marie Curie started the Cure Institute in 1909, I think we're able to cure about 1% of cancers. We've gone a long way. Today, it really depends. There is a very wide spectrum of cancers, and our ability to treat them varies greatly. But on average, it's probably something like 60%, 66% that we're able to provide a cure for. I think with AI, we really have the ability to not take another 100 years to get better, but actually maybe get to 80%, 90% of cancers cured, and that would be absolutely amazing. So I don't know if it will take us 5 years. I think healthcare, has taught us to be very humble, but I do believe AI will really accelerate the way at which we make, real progress for some of the toughest diseases that we have to tackle.
Yeah, I like those. And also, earthquakes are hard, as you know. We've done floods, made a lot of progress in predicting floods, but earthquakes are hard. Pushmeet, what do you want to solve?
I think if you think about basically the human civilization, we define human civilization in terms of like the Stone Age and the Iron Age and the Bronze Age, and depending on who you ask, we are living through the Silicon Age or the Plastic Age. But the ability to transform energy, that is essentially the power that humanity has today, right? If you can discover new materials like a room temperature superconductor, that will unleash sort of a power right? That gives us a number of different, really expands our action space in terms of when we deal with problems of energy consumption, climate change, and so on. So a room temperature superconductor is my sort of practical fusion is also there. And then finally on the math side, I'll take 3, is one of the Millennium Prize math problems would be a good bonus as well.
Which one? The Riemann hypothesis?
There is one that is my favorite, but I can't disclose it.
Okay. All right. Well, I think one of the things I like about the list that most of you came up with us on your mind is I think a lot of those problems have what you might call a root node aspect to them, which means if you can solve it, it opens up so many other things for solutions, products, others to innovate on. That's always been one of the extraordinary things about AlphaFold, because it just opens up so much more for others to chime in on. Well, to help me in thanking my panel, I think they're extraordinary work.